Hey there, and welcome. If you've got a radio communications exam on the horizon, then you have definitely come to the right place. In this explainer, we're going to break down the absolute fundamentals of how radio transmitters and receivers work right from the very beginning. So let's just dive right in.
All right, so here's our game plan. We're going to start with the big picture, the 30,000-foot view. Then we'll dive deep into part 1, the transmitter. After that, we'll tackle part 2, the receiver. We'll also look at some cool little circuits for fine-tuning, and then wrap it all up with a quick recap and a couple of questions to see what you've learned. Sound good?
So let's get into the big picture. What's the fundamental mission of radio? Well, when you boil it all down, the goal of any radio system is actually super simple. It's just about getting understandable information, whether that's a voice, a simple beep, or even some data from point A to point B, without any wires. Yep, that's really it.
Now, to make that happen, you need two main players on the field. Think of it like a conversation. You've got the transmitter, that's the one doing the talking. Its whole job is to create and send out a radio signal that's carrying some kind of information. And then you've got the receiver, that's the listener. Its job is to catch that signal and then decode it to figure out what the message is. Simple, right? One talks, the other listens.
Okay, let's kick things off with part 1, the transmitter. We're going to look at how this thing works, building our way up from sending just a simple little beep all the way to transmitting a clear human voice. All right, so the simplest type of transmitter, the granddaddy of them all, is the continuous wave transmitter, or CW for short. Honestly, the best way to think about it is like a flashlight. It's just creating a constant beam of radio energy, and all you're doing is turning it on and off to make short or long pulses, the dots and dashes of Morse code.
So let's actually look at how this thing is built. You see that block diagram? On the left, you've got the oscillator. That's what creates the basic radio wave. From there, it goes through a buffer, which is just there to keep the wave nice and stable. Then it hits the power amplifier, which, as the name suggests, beefs it up and gives it the muscle to travel a long way. And see that thing labeled key? That's literally just the on-off switch that makes the dots and dashes. That's all there is to it.
So you might be wondering, why are we still even talking about this? It sounds so basic. Well, there's a good reason. It's because CW is incredibly tough. A simple on-off signal can cut through heavy noise and static when a normal voice call would be totally unintelligible. It's super efficient, super reliable, and absolutely fantastic for long-distance communication.
Okay, so dots and dashes are great, but they're kind of limited. What if we want to send something more complex, like a human voice? Well, for that, we need to modulate the signal. And the first method we're going to look at is a classic, amplitude modulation, or AM. All this means is that we're going to take our radio wave and vary its height, its amplitude, to match the shape of the sound wave from a voice.
Take a look at this diagram. You can see there are basically two things happening at once. See that top path? That's creating our steady radio frequency wave, the RF carrier. Now look at the bottom path. That's taking the audio frequency, the AF signal, from a microphone. And where do they meet? They both get fed into the power amplifier. You can think of the amplifier as the place where the voice signal gets stamped onto the radio wave, right before it's sent out to the antenna.
Of course, changing the wave's height isn't the only way to get the job done. There's another really common method you've definitely heard of, frequency modulation, or FM. With FM, we keep the amplitude, the height of the wave, totally constant. Instead, we vary its frequency. We make the waves get a little faster or a little slower to match the sound of the voice.
Okay. Now for a really clever upgrade to AM. So engineers figured out that standard AM is actually pretty wasteful. See, it creates the main carrier wave plus two identical copies of the information, which we call sidebands. That's redundant. So they invented single sideband, or SSB. It's a super efficient version that just gets rid of the main carrier and one of those sidebands, and then crams all the power into the one remaining sideband. It's kind of like proofreading a letter and deleting all the repetitive words before you send it.
And the result is, well, just look at this comparison. It's a huge difference. A normal AM signal might take up about 6 kilohertz of space on the radio spectrum, but an SSB signal, carrying the exact same voice information, takes up less than half of that, under 3 kilohertz. That means you can literally fit more than twice as many conversations into the same slice of airwaves. That's a massive deal.
So, just to recap, this is why SSB is so important. It gives us two key advantages. Number one is power savings. You're not wasting any energy on parts of the signal you don't need. All the power goes into the part that actually carries your voice. And number two is bandwidth savings. Like we just saw, it lets us pack more signals into our crowded airwaves. It's all about efficiency.
All right, that's it for the transmitter.
Our signal is now out there, flying through the air. So let's flip the script and talk about part 2, the receiver. How do we actually hear the message on the other end?
You know, it doesn't matter if it's a simple crystal radio or a super high-tech gadget, every single receiver on the planet has to do these 4 basic jobs. First up is reception. That's just the antenna grabbing the signal out of the air. Second is selection. That's you tuning in to the one frequency you actually want to listen to. Third is detection. This is the cool part, where it cracks open the radio wave and pulls out the audio. And finally, number 4 is reproduction, turning that electrical signal back into sound you can hear.
Okay, so when it comes to receivers, there is one design that is, by far, the most common. It's called the super heterodyne receiver, and its core idea is absolutely genius. Instead of trying to deal with all the millions of different frequencies coming in, it does something really clever. It takes whatever frequency you've tuned to and converts it down to one single standard lower frequency. We call this the intermediate frequency, or IF. And doing this makes the rest of the process way easier.
So how does it do that? Let's follow the signal path on this diagram. The signal comes in from the antenna and gets a boost from the RF amplifier. Then it hits the most important stage, the mixer. In the mixer, our incoming signal gets combined with a totally different signal that's being generated inside the radio by the local oscillator. And when you mix those two together, you create a new frequency. That's our intermediate frequency. And that whole process of mixing frequencies is what we call heterodyne.
So we've got a basic receiver now, but let's be real. Signals in the real world are messy. They fade in and out, there's static, there's noise. So to get a perfect signal, we need a couple of extra circuits to help us fine-tune everything.
First on our list is something called automatic gain control, or AGC. Have you ever been listening to a faraway AM station in your car and the volume seems to get louder and softer? Well, without AGC, it would be 1,000 times worse. The volume would be jumping all over the place. AGC is basically an automatic volume knob for the receiver. It listens to the signal strength and constantly adjusts the amplification to keep the volume you hear nice and steady.
And here's another problem. What happens when nobody is talking? All you hear is that horrible ksh of static, right? So annoying. Well, that's what the squelch circuit is for. Think of it like a bouncer at a club. It keeps the speaker muted as long as it only hears noise. But the second it detects a real strong signal, it opens the gate and lets the audio come through loud and clear.
Phew, we have covered a lot of ground. So before we wrap this up, let's do a super fast recap and then a quick quiz just to make sure all these new ideas are locked in your brain.
All right, lightning round. Let's hit these key terms. First, heterodyning. Remember, that's just mixing two signals to create a new one. Next up, selectivity. That's how good your receiver is at picking out the one station you want and ignoring everything else. Then there's fidelity. That's all about how accurately the receiver can reproduce the original sound. And finally, suppression. That's the trick SSB uses to get rid of the parts of the signal it doesn't need. Got it? Good.
Okay, time to test yourself. Question number 1. Can you name the 4 basic types of transmitters that we talked about today? Take a second to think. All right. The answer is continuous wave, or CW, amplitude modulation, AM, frequency modulation, FM, and of course, single sideband, SSB. How'd you do?
And our final question. What is the main job, the primary function, of that whole heterodyning thing we talked about in a super heterodyne receiver? The answer is, it's all about converting that incoming radio frequency down to a fixed, lower intermediate frequency. Why? To make it much easier to process. Hey, if you got both of those right, you are in fantastic shape. Thanks so much for joining me, and seriously, good luck on that exam. You've got this.